This is lesson 4.7 of acids and bases for chemistry 12. The topic is Kw. Kw stands for the self-ionization of water. Kw equation can be written in two ways. The first one here, the second one at the bottom. The only difference is in the second equation we have balanced it with a 2 to make up H3O on the product side of the equation. To write a Kw expression, you do products over reactants. So exactly like we used to do with KSP and KEQ. We'll remind you that water on the reactant side is a liquid, so we don't have to write it in our Kw expression, which means we have no denominator down here. It's just a nice, simple, single-line expression. Same is true for the second expression, the second equation. There's our H3O and OH, both on the product side, multiplying in square brackets for molarity. And H2O here is a liquid, so again, there's nothing underneath the equation. Those are the two forms of the Kw expression. Kw expression is the basis of our pH scale. A neutral solution has equal H3O and OH minus. Acidic has greater H3O, and basic has greater OH minus. So if you need to take any of those notes down, just pause. And the last piece about Kw is that it has a number associated with it. The number for Kw is 1.0 times 10 to the minus 14. So this is a constant at 25 degrees. And the minus 14 will link into logs and the pH scale later in the unit. But if you do log of 10 to the 14, you get the number 14, which is why we have 14 steps on our pH scale. Okay, we'll start with some equations for Kw in calculations examples. A neutral solution, H3O plus equals OH minus. So I'm going to make my equals a little better. And they would like you to find the concentration of each ion. Each of H3O and OH minus are 1 to 1. So I'm going to call both of those X. So I can take those X's and substitute them into my Kw expression here. And I can solve for X. So 1.00 times 10 to the negative 14 equals X squared. And then I can take the root on both sides like that. And as an answer, I get 1.00 times 10 to the negative 7 is equal to X. And just like in KEQ, it's asking you for each ion, so you want to go back at the end and list your ions that you had. And both of these are 1.00 times 10 to the minus 7. Okay, another example gives us an amount of acid for H3O. So the question tells us it's an acid solution. It dissolves in water and contains H3O of 0.001, or 0.01. Calculate the OH minus. Okay, so first thing I would like to do is write my Kw expression. So H3O plus times OH minus. Going to fill in the numbers I know, which is H3O and Kw. Doesn't give me a temperature, so I'm going to assume it's 25 degrees and use 1.00 times 10 to the minus 14. My H3O in my question is 0.01 molar, and my OH minus, I can call that X, or I can just leave it as OH minus since it's the only variable. And my answer comes out to 1.00 times 10 to the minus 12, which is my concentration of OH minus. Okay, self-ionization of water is endothermic. Oh, I lost a little bit of my equation here. This should read 2H2O plus 59 kilojoules makes H3O plus OH. Okay, so it is endothermic, which is shown here by my heat term on this side. And now we have to bring a little bit of Le Chatelier back into here. So if we remember our Le Chatelier's principle, If we increase the temperature, what happens to the equilibrium? So I'm going to push this up. My equilibrium is going to shift to my product side. So this way, or to products, which means I have more H3O plus and OH minus. This we have been calling what we called product heavy when we did our KEQ expressions. Okay, so if we're product heavy, we have more products. So the value for KW will increase, or KW will be greater than 1.00 times 10 to the minus 14. The next part of our question asks us to decrease our temperature. So I'm going to have to erase my solving for the first part here. If I decrease, bring this down, my equilibrium is going to shift this way toward my heat term. So it's gone this way, or to my reactants. Now I have less product, or less of the ions H3O and OH minus. And in our previous unit, we called this product light. Okay, so if you're becoming product light, what happens to your KW? So less products. Then my KW will decrease. And it could be written as KW is less than 1.00 times 10 to the negative 14. Unless you are told otherwise, you're going to assume that it's 25 degrees and that the KW is 1.0 times 10 to the minus 14. You should pause the video now and complete the quick check. I will scroll down and you can check your answers. Okay, and we have one last KW calculation here to show you how to complete. So my question in example 1 wants to know the H3O and the OH minus in a 0.001 molar solution of HCl. So the important thing is to know that HCl is one of your top 6. It's a strong acid, which means it dissociates 100%, and that means that this value for H plus is actually going to be the same as my concentration of acid. So if my HCl is 0.001 molar, that means my H plus is also 0.001 molar. That's what 100% dissociate means. And my Cl minus is also 0.001 molar, because these are 1 to 1. Okay, and my H plus is the same as H3O when we are talking about an aqueous acid dissolved in water. Okay, so to complete our equation for Kw, I'll fill in what I know. Kw is 1.00 times 10 to the minus 14. My H3O value is 0.001 molar. And I am solving for OH minus in this case. So with a little bit of math, I come out to 1.00 times 10 to the negative 11 is equal to my OH minus. Okay, and then this question wanted to know as an answer H3O plus and OH minus. You want to make sure you make those answers really clear. Your H3O plus was 0.001 molar, or if you wanted 1.00 times 10 to the negative 3. Truly, there's not enough sig figs listed to call that 1.00, so I'm just estimating. And this one, if you take your sig figs from the negative 14 number, 1.00 times, oops, sorry, that should be negative 11. And this question is rather ambiguous in the sig fig, so it would be okay to report that to 1 sig fig. Okay, and our last example, it is asking for 0.025 molar NaOH. So it wants to know H3O, however, it's given us OH minus. So the question is, acidic, basic, or neutral, support with calculations. So what it wants you to do is use some numbers to show that NaOH is basic. So the first thing we need to do is know that NaOH is a strong base. It's one of the bottom two on the table, which means it's 100% ionized. Okay, so that's all column 1 and column 2 with OHs. So like it could be written as it's a base. So anything that's like BOH is a generic base, or B bracket OH bracket 2. That's column 1 of my table, and that's column 2 of my table. 100% ionized means the number given in the question, which is 0.025, is going to be my Na plus and my OH minus. From here, it's a simple fill in. You can take a minute to pause and check your answers and check your math. And in the end, we wanted to show that, use numbers to show that the solution is basic. So here's my final answer. My solution is basic, and the reason is that my H3O concentration is less than my OH minus concentration. The OH minus is bigger, which makes my solution basic.